I am going to show you how to identify the mixed strategy Nash equilibrium in a simultaneous move game with two players. Let us consider a game between a taxpayer and the government. The taxpayer has to decide whether to cheat on taxes, and the government has to decide whether to audit him. So to understand this game, let us first begin with the payoff of the taxpayer. I am going to assume that the taxpayer is considering underpaying taxes by $1,000. Hence, if he cheats and is not caught, his payoff is $1,000. Now, if the taxpayer cheats but is caught, then he will have to repay the government this $1,000 that he cheated. Not only that, he will have to pay a fine of $1,000. Hence, if the taxpayer cheats and is caught, his payoff is negative 1,000. Finally, if the taxpayer does not cheat, his payoff is assumed to be 0. Now, let us consider the government's payoff. There is a cost associated with each audit. I'll assume that this is $500. I'll also assume that an audit is able to perfectly detect all cheaters. Let us now consider the gross payoff of the government, that is its payoff excluding the audit cost. If a taxpayer cheats and is caught, then the government imposes a fine of $1,000 on the taxpayer. Hence, the gross payoff of the government in this case is $1,000. On the other hand, if a taxpayer cheats but is not caught, then he escapes by underpaying taxes by $1,000. Hence, the government's payoff in this case is negative 1,000. Now, from the gross payoff, we can compute the net payoff of the government by deducting the audit cost whenever an audit is conducted. Based upon the description of the story that I mentioned, the payoff matrix of the game is given by this one that you see in your screen. If the taxpayer cheats and the government audits, then the taxpayer is caught. Hence, his payoff is negative 1,000. The government's gross payoff is positive 1,000, but it has to bear the audit cost of 500. Hence, the government's net payoff in this case is only positive 500. Now, if the taxpayer does not cheat but is audited, then the taxpayer does not have to pay a fine. Hence, his payoff is 0. But the government has to bear the audit cost of $500. Hence, the government's payoff in this case is negative 500. Third, if the taxpayer cheats but is not audited, then the taxpayer's payoff is 1,000 because he gets away by underpaying his taxes by $1,000. As far as the government is concerned, it loses $1,000 in taxes, but it does not have to worry about any audit cost. Hence, the government's net payoff in this case is negative 1,000. And finally, if the taxpayer does not cheat and the government does not audit, then the payoff of each of them is 0. I am going to show you how to identify all Nash equilibriums in this game, both pure as well as mixed. So let us begin by assuming that the taxpayer strategy is to cheat with probability alpha, and the government strategy is to audit the taxpayer with probability beta. We can now compute the taxpayer's expected payoff. Suppose the taxpayer cheats, then his payoff will be either negative 1000 if he is caught or positive 1000 if he is not caught. The chance that this taxpayer will be caught is beta, and the chance that he will not be caught is 1 minus beta. Hence, the taxpayer's expected payoff from cheating is negative 1000 times beta plus 1000 times 1 minus beta, which can be simplified to 1000 minus 2000 times beta. If the taxpayer, on the other hand, does not cheat, there is no uncertainty about his payoff, and his expected payoff in that case is 0. We can now determine the best response function of the taxpayer. The best response function of the taxpayer will tell us the best way the taxpayer can respond to any choice of beta by the government. In order to determine the best response function of the taxpayer, we will have to compare his expected payoff from cheating and from not cheating. By making this comparison, it turns out that the taxpayer's optimum strategy is to cheat if it is the case that beta is less than 0.5. Now remember that if the taxpayer decides to cheat, then that is equivalent to saying that he should set his alpha as equal to 1, because alpha is the probability of cheating. We can also find out that the taxpayer's best response is to not cheat if it is the case that beta is greater than 0.5. Now, if the taxpayer does not want to cheat, that is equivalent to saying that he should set alpha equals 0. Finally, if beta is equal to 0.5, then the taxpayer is indifferent between cheating and not cheating. That is, both are equally preferable. So in this case, any value of alpha between 0 and 1 is optimum. Let us plot the best response function of the taxpayer in this diagram. Alpha is plotted along the horizontal axis and beta is plotted along the vertical axis. And the best response function of the taxpayer is shown in red. As you can see, if beta is less than 0.5, then the optimum value of alpha is equal to 1. If beta is greater than 0.5, then the optimum value of alpha is 0. And finally, if beta is exactly equal to 0.5, then the optimum value of alpha is anything between 0 and 1. So that is shown by the horizontal segment. Now let us consider the government. If the government audits, then its payoff is either 500 or negative 500, depending upon whether the taxpayer cheats or not. In this case, its expected payoff can be simplified and written to be equal to 1000 times alpha minus 500. On the other hand, if the government does not audit, its expected payoff is negative 1000 times alpha. We can now determine the best way the government can respond to any choice of alpha by the taxpayer. In order to do that, we need to compare the government's expected payoff from auditing and from not auditing. By comparing these two numbers, it turns out that if alpha is greater than 0.25, then the government's best response is to audit. This is equivalent to saying that if alpha is greater than 0.25, then the government should set the value of beta as equal to 1. Now, if alpha is less than 0.25, the government's best response is to not audit. This is equivalent to saying that if alpha is less than 0.25, then the government should set beta as equal to 0. Finally, if alpha is equal to 0.25, then the government is indifferent between auditing and not auditing. Hence, in this case, any value of beta between 0 and 1 is optimum. We can now plot the best response function of the government as well. This is shown in green. As you can see, if alpha is less than 0.25, then the optimum value of beta is equal to 0. If alpha is greater than 0.25, then the optimum value of beta is equal to 1. And finally, whenever alpha is exactly equal to 0.25, then any value between 0 and 1 is optimum for beta. Hence, this green curve plots the best response function of the government. A Nash equilibrium is a collection of strategies where players play mutual best responses. Hence, every intersection of these best response functions is a Nash equilibrium. In this specific example, it turns out that there is only one intersection of the two best response functions, and hence there is only one Nash equilibrium in this game. In this Nash equilibrium, the taxpayer cheats with probability 0.25 and the government audits with probability 0.5. Hence, this is a Nash equilibrium in completely mixed strategies. There is no pure strategy Nash equilibrium in this game. We can also think of the interpretation of this result. Suppose in the real world, there are a large number of taxpayers identical to the one that was discussed in the story. In that case, our model predicts that around 25% of the taxpayers will cheat and the government will audit around 50% of them.